Okay, so this is review for related rates. So here, I'm going to read number 35 to you. A retail store estimates that weekly sales S and weekly advertising cost X, both in dollars. So right there, it's identified what the variables mean. So that's okay to write that down. It's all right to say, this is number 35. It's all right to say S equals sales and X equals advertising cost. I'm a big fan of write more, not less, as long as you write it kind of in an organized fashion. And then it says the current weekly advertising costs are $2,000. So current weekly advertising costs are $2,000. If I wanted to write that in terms of a variable equals a number, which variable would I pick? Well, it's advertising costs, so I'm going to say X equals 2,000. The next sentence says, and these costs are increasing at the rate of 300 per week. So increasing at the rate of, that makes you think of what? Derivatives. I heard it somewhere. Yes, derivatives. So increasing at a rate of per week, that's per time. So that tells me that dx dt equals 300. And I get that by seeing that the costs, x, the costs, are increasing at the rate of, that means derivative, so dx dt. And then it tells me that they are related this way. Oh, what was the question? What is that part, right? The find part. So this is kind of our know section. This is everything we know, but let's go back and see what we're trying to find. That's always worth finding. Related by, find the current rate of change of sales. So rate of change of sale, what I need to, so find what? What am I trying to find in terms of variables? DSDT. Sales, rate of change of. So that tells me DSDT. So I don't know what problem this is, right? Because this is on a test and they're all kind of jumbled up, and so I don't know necessarily what kind of a problem this is. So when I look at everything that I've written down, because I've translated all the English sentences into math, I'm seeing a rate and a rate. And they're both with respect to time. So that suggests to me that I have a related rate problem. Okay? The first step to doing a related rate problem is to relate the variables. Sometimes we have to draw a picture for that. Ladders, boats moving towards a dock, oil spill, circle, whatever. Sometimes we have drawings to make. Here we don't. Here, this step's already done for you. We already have relate. So what are we relating? The variables. The variables are these pieces here. I have to relate the variables first. So I've already done that. So I'm going to write that down again so I can be right under it. Okay, so the first step is to relate the variables. The second step is to relate the rates. It's important in this variable step that everything that can change stays a variable. If it can vary, it's a variable. Okay, so just because I know that the current value, the current advertising costs are $2,000, that doesn't, right, that can change. So because it can change, I can't plug in that number yet. So anything that varies stays a variable in these steps. So the next step is to relate the rates. So what rates am I relating? In this case, dsdt and dxdt. So writing them down like this or on your list like this tells you the next step. I've related the variables, right? I've done this part. So what's left to do? That part. That's my instruction. I need to ddt the entire equation. And I'm being a little picky on some of your assignments. I'm not taking points off for it. I'm just kind of writing instructions. Do not write this. No, that's a bad example. I need another time to remind me to make a comment about how you write the answer. So what I'm going to do here is I'm going to ddt the entire thing. And remember, when I write ddt, that's an instruction that says, this is a verb. It says, do the derivative with respect to t. Okay, so I'm looking at this. Derivative of s with respect to t. Do the variables match? No. So that's just a ds dt. Okay, when the variables don't match, I'm going to have this extra. It's kind of part of a chain rule, but this is so simple. So this one goes here. 60,000 derivative of that is 0. Minus 40,000 times, what do I do with that? That just carries through, right? Addition, subtraction, multiplied by constant carries through. So minus 40,000 times the derivative of this. So let's just pull that off to the side and consider that. I need to find the derivative of that. Is it a basic? The first question you always ask is it a basic? And how do I know if it were e to the plane x, that would be a basic? It's not a plane x, so it's not a basic. Okay, so if it's not a basic problem, that means it's a composite function, so we have to use chain rule. So we have to identify inside, outside. So ways that you know what the inside, ways to know that. One is when I say to the. E to the, what follows next, if I were saying it in English, what follows next is the inside. So this right here is the inside, and this e to the x is the outside. So derivative, so remember when we're doing chain rule, we take the derivative of the outside first, times the derivative of the inside. So the derivative of an e function is itself, including the inside. So I'm going to start here and just write, that's kind of fun about exponential functions. You just write it. So the inside stays alone. We don't mess with that yet. So now I'm taking this right here is the derivative of the outside. So I've done that. Now I need to multiply by the derivative of the inside. Okay, so what is the derivative of the inside? That's just this piece. So negative point, so parentheses, negative 0.0005. Is there any more? Yeah, I'm doing it with respect to time. So I need a dx dt. Because this is not a t. So so I have to do that part. So the derivative is going to be 0.0005 dx dt. So now I have related the variables, and I have related the rates. So now the question is, go back and see what I'm trying to find, ds dt. And what else do I know? I know x, and I know dx dt. So let's look in here and see, do I have all the pieces I need? I have this one, and I have that one. I'm trying to find that one. So now it's just a matter of just plugging in. So this becomes a plug and chug at this point. I don't remember what the answer is. So the important part about related rates. One, recognizing that it is a related rate, and the way we know that is because we start seeing rates, and they're with respect to time. Okay, this is different than marginal analysis. That's a whole separate thing. This is related time rates. So once I start seeing some DDTs, I know I need to relate the variables first. Anything that varies stays a variable. Then relate the rates by taking the derivative with respect to time of the entire equation, and then make sure that I have all the pieces I need and substitute. Sometimes I won't have all the pieces we need, and the example we're going to do in class today later will take care of that. Yes?
Why took the derivative of the outside, it kept the exponent?
Because when we do the chain rule, that's what we're doing. So when we do the chain rule, that's just how the chain rule works. When you take the derivative of the outside, in parentheses, what you're remembering is that the inside stays the same. You're not dealing with that yet. Okay, that's just part of the chain rule. So you take the derivative of the outside, leave the inside alone. Deal with one thing at a time. Then, now you're going to deal with the derivative of the inside. So this is just part of the chain rule.
I'm just kind of confused, like, why would it still remain an exponent?
Well, this is not an exponent anymore. So it's just the exponent there. Why does this stay an exponent?
Yeah.
Because when I know that the derivative of e to the x is e to the x, so the x stays in the exponent. That's just part of that definition. So when I do the derivative of the outside, I have the same pattern. Oh, this is a perfect time. All right, hang on. No, I have a good example of you can thank your classmates who came to see me. I came up with a good way to think about this. So this is kind of stepping out of order, but this is a good time. So let's look at some functions and their derivatives and how chain rule applies and how the pattern comes through. And we're going to do it for exponentials and we're going to do it for logs because those are the ones that seem to give everybody the most trouble. So we're going to start with a function here. I'm going to make two columns and its derivative here. Okay, so we're going to start with e to the x. Derivative of e to the x is e to the x. We love that. That's great. Derivative e to the 3x. E to the x is a basic because it just has an x. E to the 3x, is that a basic? No, because that's no longer just a 3x. So that means we take the derivative of the outside, leaving the inside alone, but derivative of an e to the x is, derivative of e to the something is e to the something, times the derivative of the inside. Yes?
So you're doing this chart in regards to chain rule?
Yes.
Okay.
Well, and even if I didn't name it, I'm just saying that if I have this function, that's its derivative. But yeah. But yes, it is using chain rule. So here's another one. E to the x squared. Is that a basic? No, because I have an x squared, not an x. So its derivative is e to the x, same thing, e to the x squared times the derivative of its inside. Let's do another one. E to the 7x cubed plus 2x. What goes here? The same thing. 7x cubed plus 2x times the derivative of its inside. What's the derivative of this inside?
21x squared.
21x squared plus 2. Okay, one more. E to the y. And I should say that these are derivatives. These are all with respect to x. So now I've changed the variable. So it's the same pattern, e to the y. E to the something all the way down, but now I need the derivative of the inside. Derivative of that would be dy dx. So we've gone from a basic through some more complicated ones to implicit differentiation. The pattern is all the same. E to the something, e to the something, e to the something, right? All the way down, times the derivative of the inside. And if I wanted to think about it, what's the derivative of this inside? So really, the pattern is exactly the same all the way down. So it's e to the something times the derivative of its inside. And if it's a different variable, that's the derivative of y with respect to x. That's actually how we read that. That's our math way of writing all those words.
I got like a question, like it's kind of stupid, but I want to ask it.
You know what? Probably somebody else has the exact same question.
So, if the derivative of x is just 1, why is the derivative of y just y prime?
Because it.
Wouldn't it be 1?
Yes, but the variables don't match.
Like 1 y prime?
Because it's doing derivative.
Right. So right. So if you had d dy of y, the variables match. That's 1. If I have d dx of y, it's 1 times the derivative of the inside. What's the derivative of the inside?
Y prime.
dy, yeah, y prime or dy dx, yeah. So it's the same thing, it's just with 1 you don't really see it. We don't really talk about it as chain rule that way. I mean, you can think of it that way, it's just simple enough. We usually just kind of go and say that the derivative of x, y with respect to x is, we just simply write that way. So let's do another set with logs. All right, so we're going to do the same thing. Same set of function and derivative with respect to x. So, ln x. Is it a basic?
Yes.
Yes, just has an x. So its derivative is what?
1 over x.
1 over x. That's one you just need to know like that fast. Okay, so here's another one. Is it a basic? No. No, because, and here's another way that you can know chain rule is coming. If I were to read this in English, a lot of times we say ln 2x, but what we really mean is ln of 2x. Of is another key word that says the inside's coming. Square root of, ln of. So this is not a basic. So I have the same pattern, 1 over 2x, times derivative of the inside, which would be 2. Okay, here's another one. Is it a basic? No, it's a composite function because it's not a plain x. So same pattern, 1 over times the derivative of its inside, which is what?
2x plus
2x plus 7, remember your parentheses. Then y. Is it a basic? No, because I'm looking at derivative with respect to x. The variables don't match, so same pattern. 1 over y times the derivative of its inside, y prime dy dx, whichever way you want to write it. So this is also, sometimes people will write it this way, because y prime is just a little easier to write. Yes?
So what do we do if the derivative is not specified? It just says find the derivative.
Oh, and that would be...
with respect to each variable in the equation?
No,
or
you can only do it with respect to one variable
Right.
at a time for the entire equation. So if it is not stated, it's usually implied that it's x. If you have y's and x's and it's not stated, it's usually implied that it's x. But that's a little sloppy. Really, it should be more specific than that.
Okay.
So one more on logs. Two ways to do this one. One way is to say, is it a basic? No, oh, first let's back up. What is squared in this? Is the log squared or the x squared?
the x.
Just the x. Remember, the exponent only applies to the thing right below it unless there's a parenthesis. So this is different than this. Completely different. Okay? So this one, I can do the same pattern. 1 over x squared times derivative of its inside, 2x. 2x over x squared, 2 over x. Let's look at way number 2, which is really important when it gets more complicated. Laws of logs tell me that I can take this and put that down in front.
Even though it's just attached to the x.
Especially because it's just attached to the x. If it were this, I couldn't do that. So, so the reason I can do that is because this is really ln of x times x. Multiplication on the inside of a log turns into addition on the outside. So that would be ln x plus ln x, 2 ln x's, which is the same as pulling the 2 down in front. Okay, so I can rewrite this as 2 ln x. Is this a basic? Yeah, it's a basic, just multiplied by 2. So its answer is 2 over x, same answer. For one as simple as this, it really doesn't matter which way you go. But when we get it to more complicated ones, being able to pop that exponent down in front changes everything, makes it so much easier. Particularly if this is, say, like 3 halves. We would really like that to be multiplied by 3 halves rather than a power of 3 halves. Okay, so we'll come back to that. All right, so I just thought this was kind of a good way to sort of see the pattern all the way down and to go from basic through chain rule into implicit differentiation and kind of see the pattern each way. Okay, so let's take a moment and talk about the test, and then we'll start on some review.